So, um, usually when you look at a massive industrial facility, like, say, a commercial food processing plant or a giant dairy factory out on the edge of town, you just see the raw architecture, right?
Yeah, totally. It's just concrete and logistics.
Exactly. You see the concrete facades, the endless line of loading docks, just the sheer scale of moving thousands of tons of material. But if you look up at the roof, you almost always see these thick, white plumes of steam just rising steadily from the cooling towers.
Right, and most of us just drive past it. We think, okay, that's just a factory doing factory things.
Yeah, it just becomes wallpaper.
It really does. We're so conditioned by that industrial landscape that we view the steam as just a binary indicator.
Right.
Like the factory is running, therefore there is steam. We process it as this completely normal, inevitable byproduct of doing business at scale.
But when you actually crack open the thermodynamic reality of what's happening inside that building, that innocent white cloud is, well, it becomes something entirely different.
It's actually a massive red flag.
Right. And so to figure out how to interpret that landscape, we are unpacking a really unusual stack of sources for today's deep dive.
We really are. It's quite a mix.
Yeah, we're looking at private engineering manifestos, blueprints for modern industrial business models, visual architecture guides, heavily inspired by the designer Dieter Rams, and we're even digging into some raw, unfiltered debates pulled straight from online physics forums.
Which is fascinating, by the way. Those forum threads get intense.
They really do. And the mission of this deep dive for you listening right now is to trace the exact physical, financial, and mechanical steps required to intercept what really amounts to a $1 trillion blind spot.
Yeah, a blind spot hiding in plain sight.
Exactly, because those companies are literally paying millions of dollars in electricity just to throw that thermal energy away into the sky. And at the exact same time, and this is the crazy part, in another part of that very same building, they are burning massive amounts of fossil fuels to recreate the exact same heat they just threw away.
It's honestly a structural business failure. I mean,
Yeah.
it's just hiding right there.
It's wild.
So we are going to explore how smart operators are taking a specific engineering mindset, something they call restorative engineering, and using it to intercept that wasted heat.
And we should clarify, this isn't just a conversation about industrial plumbing, right?
No, not at all. We're going to trace how this philosophy bridges the gap between heavy physical machinery, financial ingenuity, and ultimately human safety and medical breakthroughs.
Right, because to really understand the hardware of recovering that wasted heat, our sources make it clear that we actually have to start somewhere completely different.
Yeah, way outside the boiler room.
We have to understand the operational philosophy that drives these engineers, and their origin story doesn't begin with a factory air conditioner. It begins on an assembly line that handles raw explosives.
Yeah, the team behind these manifestos, they found themselves observing factory workers whose daily 8-hour shift involved manually handling volatile explosive materials.
Just imagine that for a second.
I mean, if you think about the psychological weight of that environment, it is staggering.
The sources describe the atmosphere in a way that is incredibly vivid. Like, they note that the workers were moving like people holding their breath.
Wow. Yeah, that perfectly captures it.
Right. The baseline emotion in that room wasn't boredom or fatigue, which you'd expect on a normal assembly line. The baseline was just pure fear.
Because the stakes are absolute.
Exactly. Imagine going to work every single day, standing over a conveyor belt, knowing that one wrong twitch, 1 millimeter of miscalculated movement, or even just, a moment of lost focus could result in a catastrophic event.
It's an environment where the human nervous system is just permanently redlined. You can't operate like that sustainably.
No, you can't. And the engineers looking at this recognized it as a profound systemic failure.
Right, because the manufacturing system was effectively externalizing the ultimate risk physical harm onto the human workers just to maintain production speed.
And the system was broken because it relied on human perfection in a situation where humans are, you know, inherently imperfect.
So this engineering team intervened, and they didn't try to train the workers to be more careful or give them better gloves or whatever. They engineered a custom industrial robotic arm to take over the task entirely.
And the visual descriptions in the sources paint a very specific picture of this machine. It's not some clunky, sparking piece of sci-fi machinery.
No, it's very sleek.
Yeah, they built a heavy-duty matte white robotic actuator set against the slate gray background of the factory. It descends, grips the heavy steel cylinder of explosives, and moves it into a lead-lined receptacle.
But the key detail they highlight is the movement itself, right?
Yes, it is perfectly damped. There is zero organic twitch, zero hesitation.
It absorbs the human risk entirely. There is no drama, no warning klaxons, just quiet, relentless mechanical perfection. The robot takes over the volatile interface, and the workers are able to step back behind safety barriers.
And the paradigm shift happens in the aftermath of that installation. So the corporate board of this explosives company looked at the new setup and they were absolutely thrilled.
Of course they were.
But they were thrilled for entirely financial reasons. They celebrated the operational efficiency, the increased speed of the line, the massive reduction in liability insurance.
The spreadsheet looked great.
Exactly. But for the engineers who actually built the robot, their metric of success had nothing to do with the board's financial report.
The only metric that mattered to the engineering team was a text message that one of the factory workers sent home later that night.
And the message simply read, "I reached home safe tonight."
That's incredibly powerful.
It is. I really see the philosophical weight of that. The idea that technology should be an active shield for human life is a powerful narrative. But, and I have to push back on the premise here a little bit, saving workers from an explosion is an undeniable visceral mandate.
Right, it's life or death.
Right. But how does an engineering team pivot from life or death safety protocols on a munitions line to, like, fixing factory air conditioners and cooling towers? The stakes seem drastically different. Are these engineers actually treating a bloated utility bill as a safety issue?
Well, it's the underlying logic that connects them. That moment on the explosives line codified a philosophy the team calls restorative engineering.
Okay, restorative engineering.
Yeah. The baseline truth they established is that real technology doesn't just replace people to squeeze out a marginal financial gain. Its primary function is to restore safety, dignity, and capability.
Oh, I see.
So now, when they took that exact unforgiving standard and applied it to the broader industrial landscape, they started looking for systems that were externalizing risk.
So they actually view systemic waste as a form of externalized risk.
Exactly. If a mechanical system is burning excessive capital, stressing the electrical grid, and dumping massive amounts of wasted heat and carbon into the environment simply because it's poorly designed,
That's a failure.
that is an unacceptable failure of architecture to them. They look at a factory wasting heat through the exact same lens they look at a factory risking limbs. Both are systems that are fundamentally broken and require a restorative intervention.
They just have a zero-tolerance policy for accepted failure.
Pretty much.
So, applying that lens to modern factories, the sources point to the thermodynamic loop as the most glaring failure of all. Let's decode the physics of what is actually happening in these buildings.
Yeah, we need to look at the massive commercial chillers used in places like dairy plants, meat processors, or large hospitality venues.
Because these facilities require refrigeration on a truly industrial scale.
Oh, absolutely. A dairy plant has to crash cool thousands of gallons of milk instantly. A meat processing plant has to keep massive warehouse floors near freezing all day, every day, so they employ enormous industrial chillers.
Right, and for those of us who aren't mechanical engineers, I want to use an analogy from the sources to explain the absurdity of how these buildings manage their energy.
I love this analogy.
It's so good. So imagine it's the peak of summer. You are driving down the interstate and you have your car's air conditioning blasting on maximum cold. But for some reason, you also have all 4 windows rolled completely down.
You're just fighting the ambient environment.
Right. You're bleeding all that cold air directly into the atmosphere. But to make it even more absurd, at the exact same time, you have a massive electric space heater plugged in and running at full blast in the backseat of the car.
It makes no sense.
None. You're paying for the gas to run the AC. You're paying for the power to run the heater, and you are trapped in a closed loop, just fighting yourself.
Yeah.
That is the essence of what the sources call the double energy penalty.
And let's translate that analogy into the actual physics of a factory because it maps perfectly.
Right.
Inside these massive refrigeration chillers, the core component is the compressor.
Yeah.
Its job is to take a refrigerant gas, something like R134A, which is very common in industrial applications, and mechanically squeeze it. And the laws of thermodynamics are totally unavoidable here.
When you compress a gas, it gets hot, right?
Exactly. When you compress a gas to a higher pressure, its temperature spikes dramatically. This creates what engineers call superheated gas.
So how hot are we talking?
By the time that refrigerant leaves the compressor, it has easily reached temperatures of 200 to 250 degrees Fahrenheit.
Wow. That is literally violent boiling heat.
Yep.
And it's just a byproduct of making things cold somewhere else in the building.
It is a massive thermal burden. Now, the factory has to do something with this 250-degree gas because the refrigeration cycle cannot continue until that gas is cooled down and condensed back into a liquid state.
Right, you have to shed the heat.
So they pipe this boiling hot gas all the way up to a condenser, which is usually sitting on the roof, and they pay for massive electrical fans to blow ambient air over a series of coils to literally vent this 250-degree heat into the sky.
Which explains the thick white plumes of steam we were talking about at the very beginning.
Exactly.
They are actively paying a massive electrical bill just to run fans to destroy valuable heat.
That is the first half of the penalty. But the second half of the penalty is happening down on the factory floor or in the basement.
Right, the space heater in the back seat.
Exactly. That same dairy plant that just threw away 250-degree heat on the roof desperately needs hot water. They need it to pasteurize the milk. They need it for clean-in-place systems to wash down the stainless steel equipment. They need it to sterilize vats.
And they typically need that processed water heated to what, about 140 to 160 degrees Fahrenheit?
Right in that range, yes.
So to get that 150-degree water, they pipe in natural gas from the local utility. They ignite it in a massive industrial boiler, and they just burn fossil fuels.
So they're venting 250-degree heat on the roof while paying to create 150-degree heat in the basement.
It's crazy when you lay it out like that.
It is a severe, almost comical thermodynamic failure. They are paying to destroy energy and paying to create it simultaneously.
When you make the invisible flows of energy legible like that, it's honestly maddening. And to really illustrate how stubborn and dense the energy trapped in this cycle is, our sources included this fascinating detour into a physics forum.
Oh yeah, the forum thread.
It's a thread where engineering students and professionals are debating the variables for a vapor compression refrigeration cycle.
The inclusion of that forum thread is brilliant because it pulls you out of the abstract theory, It shows you the raw friction of engineering.
Yeah, it demonstrates exactly how hard it is to actually get rid of this heat.
So you have this one user, Don, who is designing a system using R134A refrigerant, and he is completely stuck. He's trying to figure out the physical dimensions of the condenser tube he needs to shed the heat.
Right, he's asking the forum for the convective heat transfer coefficient.
And the responses from the other engineers are just a massive deep dive into fluid dynamics and thermodynamics.
It gets so technical.
It does.
Huh.
They are bringing up the Rayleigh number, which deals with buoyancy-driven flow. They are calculating the Nusselt number to understand the ratio of convective to conductive heat transfer across the boundary layer.
I mean, they're factoring in the Prandtl number too, right?
Yeah.
To account for the kinematic viscosity of the air at different temperatures.
Exactly. It reads like a completely different language.
It really does. But what becomes clear as you read through their debate is that they are realizing that air is actually a terrible conductor of heat.
It's essentially an insulator.
Right. One of the experts on the forum points out that if the Don tries to use a standard, bare, smooth copper tube to dissipate the compressor's heat into the ambient air, that tube would have to be hundreds of feet long.
The math proves that a simple, smooth pipe cannot shed the thermal burden. The boundary layer of the air just resists the heat transfer.
Which is why real industrial condensers require massive heat sink arrays.
Yes, they have to attach hundreds, sometimes thousands of thin aluminum fins to the copper piping to artificially expand the surface area just to force that heat out into the atmosphere.
So this highly technical forum debate actually proves our core point. The energy trapped in that state between the compressor where it gets hot and the condenser where it finally cools down is incredibly dense.
It is a high-grade, violent thermal energy, and industries are treating it like an annoyance to be managed rather than an asset to be captured.
Which brings us to the mechanical intervention. We've identified the absurdity of the double energy penalty. We understand the restorative philosophy that demands we fix systems that externalize waste. So how do we practically intercept this heat before it hits the roof?
The hardware fix is surprisingly elegant. You don't have to overhaul the factory's entire HVAC system or rip out the boiler room.
Thank goodness.
Right. The fix is a localized intercept called a desuperheater.
The desuperheater. Okay, how does it work?
It is the physical manifestation of restorative engineering. You basically install a specific type of heat exchanger directly on the discharge line.
So you're catching it in transit.
Exactly. You catch the hot gas after it leaves the compressor, but before it travels all the way up to the condenser on the roof.
The visual guide in our sources paints a cinematic picture of how this works in a mechanical room. Imagine looking at a macro view of heavy-gauge copper conduits. The top pipe is radiating this deep amber heat.
That's the 250-degree gas fresh from the violent compression cycle.
Right, and just below it is another pipe, and this one is frosted white with condensation, carrying cold processed water from the factory floor.
Two extreme states of energy passing right by each other.
Exactly. Then, the mechanism is engaged. A heavy steel valve turns precisely 90 degrees. That amber thermal energy from the top pipe is diverted. It shifts its path into a titanium plate heat exchanger that is sandwiched between the two pipes.
And these titanium plates are designed for counterflow heat exchange, maximizing the surface area while keeping the refrigerant gas and the processed water physically separated. You definitely don't want those mixing.
Right. The moment that 250-degree gas hits one side of the plates, the frost on the lower water pipe instantly melts. The cold water absorbs the thermal energy from the gas and transforms into a warm, steady flow of 150-degree processed water.
The superheat from the refrigerant is literally injected directly into the cold processed water.
It's just elegant physics.
It really is.
So let's break down the operational costs, because this single localized intervention creates a cascading financial impact that completely changes the economics of the building. Focus on the practical steps for implementing a desuperheater system here. How does it actually reduce the operational costs?
Well, the financial implications happen on both ends of the system. First, let's look at the boiler room down in the basement.
Okay.
Because you are now preheating, or entirely heating, that processed water using the waste heat scavenged from the compressor, the facility suddenly has a massive supply of 140 to 160 degree water for effectively zero cost.
They just inherited an unlimited supply of free hot water.
Yes. And the immediate result is that their natural gas consumption at the boiler drops drastically. In some optimally sized facilities, the boiler might shut off entirely during production shifts.
That is huge.
It's an immediate, massive slash to their operating expenses, directly impacting their bottom line.
So they stop paying the gas company to create heat. What is the impact on the cooling side? Because you mentioned it works on both ends.
Right. The second win happens back at the refrigeration loop. Because you have intercepted that 250-degree gas and sucked the majority of the heat out of it to warm the water, the gas is already cooled down significantly before it ever reaches the condenser on the roof.
Ah, so the condenser doesn't have to work as hard to finish the job.
Exactly. You have relieved the thermal load on the cooling tower. Those massive electrical fans we talked about earlier, they can spin down. They use way less electricity.
That makes total sense.
Furthermore, because the whole system is running cooler and with less pressure resistance, the electrical draw of the compressor itself actually falls. The compressor becomes mechanically more efficient.
So you stop paying to destroy energy on the roof, and you stop paying to create energy in the basement. The thermodynamic is finally balanced.
It is a total victory over systemic waste.
Which logically leads to the biggest question of this entire deep dive.
I know exactly what you're going to ask.
Right. If I'm listening to this, and the physics are this obvious, and the savings are this dramatic, why hasn't every factory in the world already done this?
It's the obvious question.
Why aren't the original equipment manufacturers, the OEMs who build these million-dollar chillers, building this intercept in as a standard feature from day one?
This is where we transition from the physics of heat transfer to the psychology of corporate structure.
The messy part.
Yeah, the sources point out that the blockage preventing this innovation isn't mechanical at all. The hardware works perfectly. The blockage is a structural blindness caused by departmental isolation within these large companies.
So the guy feeling the pain of the monthly gas bill isn't the guy holding the checkbook for the new equipment.
Precisely. In almost every large industrial facility, the budget used to buy new equipment, their capital expenditure, or CapEx, is completely isolated from the budget used to pay the monthly utility bills, their operating expenditure, or OpEx.
It's the classic corporate silo trap.
It really is. The facility manager is the one sweating over the painful, $50,000 monthly natural gas bill. They desperately want to lower it, but they don't have the authority to spend $200,000 to buy and install a commercial desuperheater system.
So they go to finance.
Right. They go to the finance director and ask for the CapEx funds. And the finance director looks at the requests, looks at the chillers running perfectly fine on the roof, and says, no, our equipment isn't broken. We aren't spending capital reserves on an upgrade right now.
Wow.
The finance department is completely blind to the fact that the upfront investment would permanently wipe out the monthly operational drain.
It's infuriating. The company bleeds cash simply because the left hand won't fund the right hand solution. But wait, what about the OEMs? Surely the companies manufacturing the chillers want to sell the most energy-efficient machines on the market.
You would assume so, but the sources reveal a hidden incentive structure there as well. OEMs generally dislike third-party desuperheaters being attached to their equipment.
Because of warranties.
Yes, liability and fluid dynamics.
Ugh.
If a contractor splices a third-party heat exchanger into the discharge line of a massive, highly calibrated chiller, it introduces a slight pressure drop. It marginally changes how the fluid moves through the system.
And the manufacturer doesn't want to own that risk.
Exactly. The OEM looks at that alteration and says, if this compressor fails in 3 years, we are not covering it under warranty because you altered the factory piping and changed the operating parameters.
So you have a total paralysis.
Yeah.
The facility manager is terrified of voiding the warranty on a $1 million machine. The finance department refuses to approve the CapEx for the upgrade, and the OEM is incentivized to maintain the status quo.
No one has the mandate to bridge the gap. Obscurity protects the incumbents.
Yeah, the utility companies are perfectly happy because they sell more electricity to run the fans and more natural gas to run boilers.
The maintenance crews are happy because the boilers run constantly and need servicing.
The only entity losing out is the facility owner, and they are too siloed internally to even see the bleeding.
Exactly.
So if you were an entrepreneur or what the sources describe as a monopoly-minded builder, how do you actually break that logjam? I mean, if you just start a company selling copper pipes and titanium plate heat exchangers, you're going to walk right into that exact same agonizing sales cycle.
Yeah, you'll spend months arguing with finance directors about capital expenditures.
This is where the business strategy becomes as elegant as the physics. The most successful operators in this space realize that they shouldn't just be hardware vendors. They need to capture what is called a control point.
It's crucial to understand this.
Let's define the control point in this context.
Yeah.
Because if it's not the pipe, what is it? Explain the importance of capturing control points to outperform competitors here.
Well, if you just sell the physical desuperheater, you make a one-time margin on the hardware, and you have absolutely no ongoing relationship with the facility. The physical hardware is just a commodity.
Anyone can bend copper.
Right. The real control point, the thing that dictates the terms of the relationship and generates long-term value, is the data.
The data generated by the heat transfer.
Yes. It is the digital integration layer that meters the recovered thermal energy. It is the software that proves, mathematically and in real time, exactly how many BTUs of waste were intercepted and how much carbon was offset. If you own that data layer, you completely change the business model.
Which brings us to the thermal energy as a service model, or TEA. Detail the financial benefits of this model for us.
So, knowing that the control point is the data, the team behind these manifestos figured out how to bypass the corporate silos entirely. They packaged the thermodynamic fix into a highly lucrative, recurring revenue model.
They realized they had to eliminate the CapEx objection right out of the gate.
Completely remove it from the conversation.
Exactly.
Yeah.
So here's how the monetization engine is structured. You, as the service provider, design a modular, IoT-enabled heat exchanger skid. And you don't just weld some pipes together, right? You design it with intense intentionality.
Yeah. The sources reference Dieter Rams' minimalist design principles here.
Less, but better.
Yes. You build this skid out of matte anodized aluminum and heavy gauge copper. You strip away every unnecessary part.
Because the visual architecture matters here. Even in a dirty boiler room, material honesty communicates reliability and precision. It builds trust.
It really does. It looks like a piece of high-end technology, not just plumbing.
So you take this beautifully engineered skid and you approach the target facility and you make them an offer that just breaks their mental model. You offer to install the entire system for zero upfront cost.
You completely bypass the finance director's objection.
The facility manager doesn't even need to ask for budget approval. You tell them, keep your checkbook closed. I'm going to install this hardware, and I, the provider, will retain full ownership of the infrastructure.
It is very similar to the model where companies install solar panels on a residential roof for free.
But instead of capturing ambient solar energy, you're capturing the factory's own wasted mechanical heat.
It is a brilliant pivot.
Yeah.
But, and here's the catch, if you give the hardware away, how do you recover your costs and build a profitable business?
That is where the data control point comes online. You install industrial telemetry sensors directly onto the skid.
We're talking about clamp-on ultrasonic flow meters and precise temperature probes.
Right. And these sensors feed data into a lightweight software layer that calculates the exact mass flow rate and temperature differential. It calculates, down to the decimal point, the exact amount of thermal energy, the BTUs, that your skid is transferring into their water system.
So you are meticulously metering the heat transfer in real time.
And then you send the facility a monthly bill for the hot water you generated for them. But the genius is in the pricing. You contractually price your hot water at a strict 20% discount compared to whatever their local natural gas utility is currently charging them to run their boilers.
The incentive structure is suddenly perfectly aligned. Let's look at the economics of that.
Yeah, let's break it down.
For the facility, they get an immediate guaranteed reduction in their operating expenses. If they used to pay the gas company, say, $10,000 a month to heat water, their gas bill drops to near zero, and they pay you $8,000 instead.
They instantly save $2,000 a month.
Exactly. They spent zero capex, they took on zero operational risk, and their OPEX goes down on day one.
And for you, the provider who owns the skid,
You secure a locked-in recurring revenue stream. You are effectively acting as a micro-utility company. But your fuel is free. It's the heat they were already throwing away. Once the cost of the hardware is amortized, your margins are incredible.
and the sources speculate on a secondary revenue stream that is potentially even more lucrative. Because you own the software layer and you're capturing all this verified telemetry, you can prove exactly how much natural gas you prevented the facility from burning.
You are meticulously documenting carbon emissions reduction.
Right, you can tokenize those verified emission reductions. You take that data to industrial compliance markets and sell those carbon credits.
It creates an entirely separate revenue stream purely from the verified data of your intercept.
You aren't just selling cheaper hot water, you are selling verified decarbonization.
Which perfectly illustrates why capturing the control point is the difference between a struggling hardware vendor and a massive recurring revenue business. By owning the infrastructure and the data, you unlock multiple revenue streams and completely bypass the departmental isolation that keeps the rest of the industry paralyzed.
Now, if a listener is hearing this and thinking, okay, the physics makes sense, the business model is bulletproof, but how do I actually prove this in the real world without raising millions in venture capital?
Right, how do you start?
The sources outline a very specific 48-hour execution plan. It's an asymmetric bet where the potential upside vastly outweighs the cost of the test.
The goal of this 48-hour plan is to move the concept from abstract theory to undeniable mathematical proof for a specific client.
Outline this 48-hour plan for us. What's the first step for conducting an initial energy waste audit?
Well, the first step is identifying the right target. You don't try to pitch a massive multinational conglomerate right out of the gate.
Keep it local.
Yeah, you look locally. You find a mid-sized dairy processing plant, a regional brewery, or a food processor. You get the facility manager on the phone, and you pitch them a completely free, zero-risk energy waste audit of their compressor room.
You promise not to disrupt production, not to cut any pipes, and not to void any warranties.
Exactly. Every facility manager will say yes to a non-invasive audit that promises to find savings.
So once you are in the mechanical room, the physical execution requires very minimal tools. The core piece of technology is a clamp-on ultrasonic flow meter.
Which is a brilliant piece of engineering on its own.
It really is. You don't have to shut down the chiller or cut into the heavy gauge copper. The meter clamps onto the outside of the discharge line and uses acoustic signals to measure the velocity of the liquid or gas flowing inside the pipe.
And you pair that with a simple industrial surface temperature probe.
Right. You walk up to a single 100-ton chiller. You locate the discharge line, that hot pipe going from the compressor up to the roof. You attach your ultrasonic flow meter and your temperature probe.
And within minutes, you have the raw data.
You can prove mathematically that this specific pipe is outputting a sustained flow of refrigerant at 200 to 250 degrees Fahrenheit.
You capture the exact telemetry of their weight.
Then you ask the facility manager for one piece of financial data, their monthly boiler fuel consumption. Basically, how much are they paying the gas company every month?
The sources call this their budget gravity.
I love that term.
Yeah, it is the massive operational weight pulling their budget down year after year.
So you have the temperature and flow rate of the wasted heat, and you have the exact financial cost of the fuel they are burning to create heat elsewhere.
You take those numbers, apply basic thermodynamics, and calculate their exact atmospheric thermal waste against their fuel consumption.
And within 48 hours of initially walking into that mechanical room, you can sit back down across from that facility manager and slide a single sheet of paper across the desk.
The proof.
Right. And on that paper, you show them exactly how many thousands of dollars they literally vented into the sky that week
Yeah.
and exactly how much they paid the gas company to replace it.
You make the invisible exhaust highly legible. And this gives you an incredible asymmetric advantage over every other HVAC contractor, consultant, or OEM who still views electricity and gas as separate, unchangeable line items.
When you use their own telemetry to show a manager that their cooling tower is actually, a geyser of capital evaporating into the air, you permanently change the paradigm of how they view their own building.
They can't unsee the waste once you make it legible.
And that is the true power of restorative engineering. It's not just about fixing machines. It's about fixing the business models and the incentive structures that allow the waste to happen in the first place.
Which brings us to the final and perhaps most profound application of this entire philosophy.
Yeah, this part blew my mind.
We've tracked this mindset from preventing explosions to intercepting wasted thermal energy. Now, the sources reveal the extreme edge of where this exact same engineering precision is being applied next.
We are moving from industrial plumbing and boiler rooms into the world of medical bioprinting.
It sounds like a leap, but it's really not.
The sources provide another one of these incredible visual prompts, and it is just stunning. Imagine a microscopic view inside a clean room. The environment is sterile, a space of absolute visual order. You're looking at a bead-blasted, dark titanium plate resting in a black void.
It is the ultimate expression of the Dieter Rams aesthetic, nothing extraneous, pure function.
Out of the darkness, a medical-grade glass nozzle descends. It moves with exact, hypnotic mechanical precision. In total silence, it begins to extrude a highly viscous, translucent blue-tinted gel onto the dark titanium plate.
And as the nozzle traces its path, the gel forms a mathematically perfect honeycomb lattice. The light catches the translucent material, illuminating it from within.
It is physically building biological tissue. It is printing the scaffolding for human cellular growth.
It is literally making hope tangible.
Now, on the surface, the obvious question is, what does a sterile bioprinter have to do with a heavy-duty robotic explosive handler or a desuperheater capturing dirty waste heat in a dairy plant?
It is the universal application of precision and intent. If you strip away the specific industry applications, it is the exact same underlying philosophy: restorative engineering.
Think about the core principles we've discussed throughout this deep dive. Absolute mechanical stability, the rejection of frantic pacing, the intentional absorption of risk.
Exactly. Whether you are building a robotic arm to handle a volatile munition so a human worker goes home safe to their family, or turning heavy steel valves to capture wasted heat so a factory stops burning fossil fuels, or mapping cellular tissue with a glass nozzle so a human body perfectly accepts a medical implant.
The mission is identical.
You are restoring capability. You are intervening exactly where complex systems fail. The author of these manifestos notes that a brilliant theoretical idea or a clever digital prompt means nothing without a resilient physical product behind it to execute it in the real world.
This team operates strictly at the intersection of mechanical design and digital logic.
They are focused on the quiet impact of building things that actually matter in the physical world. They ignore the digital distraction, the endless hype cycles of the tech industry, the empty buzzwords.
They just put their heads down and build for safety, for thermodynamic efficiency, for human restoration.
And yet, despite the profound, world-changing nature of this work, the author grounds the entire manifesto with a really brilliant piece of self-deprecating humor.
I love how the sources end. It's the ultimate reality check for an engineer. The author writes that you can build robotic explosive handlers that save lives. You can engineer massive IoT networks that capture trillions of BTUs of wasted heat and offset tons of carbon. And you can map cellular tissue on medical bioprinters to literally rebuild the human body, and your mom will still just tell her friends that you fix office printers.
Mom still thinks I fix office printers. She has a point. It is such a necessary way to diffuse the intensity of the engineering.
It shows that they haven't lost touch with reality.
Yeah.
The work is deadly serious, but they don't take themselves too seriously.
It's the posture of what they call the quiet architect. You don't need the validation of tech blog headlines. The work speaks for itself in the physical world.
Right. The text message from the factory worker saying, "I'm safe," is the validation. The telemetry showing zero-cost hot water and reduced emissions is the validation. The perfect biological lattice is the validation.
What a massive journey we've been on today.
We really have. We started on a terrifying factory floor watching workers handle raw explosives, which birthed the philosophy that technology must actively restore human safety, not just replace human labor.
We then apply that unforgiving standard to the thermodynamic failure of modern manufacturing. We expose the absurdity of the double energy penalty venting 250-degree heat into the sky while simultaneously burning fossil fuels in the basement.
We looked at the specific mechanics of the desuperheater intercepting that waste. We explored how departmental isolation between CapEx and OpEx budgets, combined with OEM warranty protections, created a structural bottleneck that paralyzed the industry.
Which led us to the elegant business solution, capturing the control point through data, the thermal energy as a service model.
Right, installing the beautifully designed hardware for free, acting as a micro-utility, and generating recurring revenue and carbon credits by selling the facility its own waste heat at a discount.
We laid out the 48-hour asymmetric bet to prove the model using an ultrasonic flow meter to calculate the budget gravity of a specific plant.
And finally, we saw how this exact same restorative mindset is currently being used to bioprint medical tissue.
The core takeaway from all these sources is that the most important breakthroughs in the coming decades will likely be quiet.
They are happening far away from the venture capital press cycles. They are happening in dirty mechanical rooms and sterile clean rooms, where smart operators fix the physical systems that externalize risk and waste capital.
Which brings up a really provocative question for everyone listening to this deep dive right now. We've spent this time talking about capturing physical thermal exhaust and stopping mechanical waste. But if you take this philosophy of restorative engineering and apply it to your own life, look at your own industry. Look closely at your own daily workflows and corporate structures.
What is your white plume of steam?
What is the invisible exhaust in your business that everyone has just accepted as normal? Is it massive amounts of generated data that you are just throwing away because you don't know how to parse it?
Is it discarded physical byproducts for your manufacturing process?
Is it redundant human effort where your team is trapped in a closed loop, burning energy to achieve nothing?
What if you built a desuperheater for that specific waste? What if you found a way to mechanically or digitally intercept it, capture the control point through telemetry or data, and turn an ignored, accepted operational drain into a recurring revenue service?
That is the mindset of the quiet architect. Find the systemic waste that everyone else accepts as wallpaper and build the bridge to capture it.
Find the waste, build the bridge. Thank you so much for joining us on this deep dive today. We hope this conversation has given you a totally new lens to view the systems, the machinery, and the business models around you. Look for the inefficiencies, reject the hype, and build for quiet impact. Until next time, keep looking at the world with the eyes of a quiet architect.